key to the porter's lodge before departing. Don't take it home with you. Luggage, bags and posters must be collected by +4 if you've left them behind. There's a taxi request list at reception, which means you have to trek all the way back over there. But please fill it out by 4 o'clock. And please return the lanyards, don't take them home as souvenirs. And tea and coffee, they're going to bring the tea and coffee here, so we won't have to trek back over there. There probably will be people coming in late, so please bunch up as much as possible. If we have too many people, there was an overflow room, the discussion room, they're setting a big screen up there, and they're going to stream Olivier over there. I mean, it's like opera. And I can't think of anything else. Catherine, is there anything else we need to announce? Okay. Are you chairing the session? Yes, and then I can hand over to you, and you can hand over to Olivier?
Yes, very quickly. So thanks again for showing up despite these difficult conditions. And today we have 2 talks before the break. And the first one is by Olivier Roustant from Saint-Etienne. Okay. Thank you very much for being here. Thank you for the invitation and for the introduction. Yes, so this morning I will talk about Gaussian process metamodeling. And this research was motivated by an application, nuclear engineering, where we have continuous inputs, but also categorical inputs. And one of them has more than 90 levels, so unusual large number of levels. So we had to do something specific for this problem. And what is nice with the Gaussian process, we can customize kernels. And this is what we did. So the idea is that we grouped levels in groups. This explains the title, so grouped kernels. Okay. Now, as you see, there are several quarters. And some of them are coming from academia, like Perrin and Deville. And we have also 3 other quarters coming from industry, from a nuclear engineering company. So Alois, Guillaume, Jean. And also we worked with Henry as an invited researcher. So I will explain more the context in 1 minute. Okay. My talk, I will first introduce the context and motivation. Then I will give you some background about Gaussian processes, especially when you have categorical inputs. How can we deal with this fact? Then I will give you more details on group covariance functions with mathematical results. So these are our main contributions. I will show you the results of the case study, and then have a discussion and a piece of perspective. Okay, so this research was conducted in the frame of a chair named Hokkaido in applied mathematics. So the domain is computer experiments, so the analysis of complex computer codes, time-consuming computer codes. And what is nice is that we have case studies, but it is not consultancy at all. Case studies motivate methodological research or upstream research. So it's really nice. And the name share can mean a lot of things, actually. But here it means a consortium gathering people coming from industry or technological research. So you know, in 3 main fields: energy, transport, and materials. And academia, and also there are 3 experts. So one of them is Deville, who steered the previous iteration of this share, which was named Redice Consortium. And also Jocelyn Granier from École Polytechnique, and Yves Deville with one of the co-authors. So in the share life, we have something very common, like PhD supervision, postdoc supervision. Something more unusual such as training sessions. So for the participant of the share, so it works like a club actually. So we have each 6 months a training session on math or on software. And also we have funding for inviting researchers. And so we invited James Hensman, which is now at Cambridge, Thomas Santner in the US, and Henry. And we invite also Guillaume Sagnol from TU Berlin. Next slide. So my co-authors of this research are coming from this company here, EMSI, Deville, and Henry. Okay. So now let's explain the problem, so the application from nuclear engineering. So we have a big computer code, and well, first let's talk about the context. We want to analyze a waste contained in a container, like that. But we cannot open the container because it is dangerous to open it. So there is a strategy using waves to know what's inside. And there is a big computer code which take it through with continuous inputs like the length from the source to the container, the density of what is inside, the form of what is inside, some geometrical parameters. And you have 3 inputs. The energy, so because it is nuclear, we have 6 levels of energy, so it is discrete. We have the shape of the waste, so very simple shape, like is it a cylinder? So the waste contained in the container. Is it a cylinder? Is it like a rectangle? Or is it a sphere? And also, this is our main problem. We have a categorical input, which is a chemical element. So we have 94 levels.
Excuse me,
Yes.
maybe it's a stupid question, but at some point the cylinder is filled, okay, but I mean they can label and they know what is inside.
No, they don't know what is inside. And the idea is to recover what is inside.
But it's already filled.
Maybe
With some
It's filled with some
It
material.
decays over time, it changes what the contents change over time.
And actually, it's the
okay,
the
there
fi-
are
the
some
final- the final-
chemical reaction happening. You mean?
there's something in it,
Mhm.
like gloves, like maybe material, and we want to identify. Actually, the final question is to identify the mass of plutonium contained in it. But we can measure only the mass times something depending on this stuff. So this is the final problem is an inverse problem. And there are 2 steps. First one is to simplify the computer code because it is too long to use. So this is the aim of this talk. And the second step is to use it to find the plutonium mass, to do the inversion problem. I will not talk about this question. Okay. There is a first work which was published in a conference paper dealing with this question, with this specific application, but with continuous inputs, so with simplified framework. And also, of course, there are, well, we have been, there was a talks about inverse problem in this workshop, and there will be also a workshop dedicated to these questions at Isaac Newton Institute on April.
Olivier,
Yes.
why did you choose to use the word metamodels?
Oh.
Not surrogate.
Not surrogates. I mean, it's my personal usage.
Ah, yeah.
But
Is it a community also that uses the computer science community?
Yeah,
I don't know. I don't really.
yeah, in optimization we always use metamodel for that sort of things.
And the other things, it's shorter to use on my slides. So.
And I think it's
That's not
quite
a
quite
good
great.
But it's absolutely equivalent to a surrogate model. Okay, so we have more details on this talk. I will give you some intuition. I will give you the main results, but I will not give you the details. So if you want to see them, you can read the preprint, which is now on archive. Okay, so now when we have Gaussian processes and we have continuous inputs and categorical inputs. So first I just recall the usual framework of Kriging or Gaussian process regression. We have three parts usually. We have a trend. So here we choose to have a constant trend. But this will be of course a good perspective to look for something different, something more specific than constant. We'll have a Gaussian process, which is centered and characterized by a kernel. And here we have a noise also. So we'll use this notation. X will denote the continuous variables, J is the categorical ones. And we have several, the levels of U, the number of levels are different. That's it. So when we have categorical inputs, there are two main families. You can have ordinal categorical inputs or nominal ones. So I think to colors, for instance, in colors you can decide that there is no order between blue, yellow, red, things like that. So you can consider it is nominal, or you can consider also that colors can be ordered because they have a wavelength. And so you can have order like this. You can choose the order in the rainbow, etc. So that this, of course, this is different. If you have an order, you can have a good connection to continuous variables. I will show you in a moment. When it is nominal, it is more complicated. So now, when we have design points, and when we estimate Gaussian process models, we obtain things like that. So there is a prediction, and also confidence bounds, or prediction bounds, more precisely. And so we have plots like this, like sausage plots. Okay. And here is an example with one continuous input here, and a categorical input with three levels. Three levels, so red, yellow, and blue. And what we see is that there is a strong correlation between these three levels. The red and blue are positively correlated, and the yellow and blue are negatively correlated. And so we aim at exploiting this correlation. So maybe I will zoom on it. So first, it's important to understand that it changes. Taking into account the correlation changes uncertainty quantification. Because for instance, look at the blue one. If you look at the blue one only, you can see that the uncertainty from this point increases as usual, but it decreases here, and then increases again, and then decreases. So it's not monotonic, which means that something happens which is different from usual kriging. It's not just the kriging on this variable. So why do we have this thing here? It's because here we have performed a Gaussian process taking into account the correlation between the three levels. And so to predict at this point, we use, of course, information provided by the blue design points, but also by the yellow ones and the red ones. And especially, this point here gives information on these two other levels. And this is why at this point, the uncertainty comes down and then increase again. Explain how also these points give information here. Okay, so it changes the uncertainty, and it's important also to understand that it allows us to perform less simulations. Because actually here, to predict on the blue one, we don't only have 3 points, but we have the points provided by the other levels which are highly correlated. So actually we have around 10 points. Okay, so now in this paper we use a formulation to build a kernel when we have both categorical and continuous inputs. So first, the thing to have in mind is that a kernel for a categorical variable is a kernel on discrete space. So it's just a matrix. And it is a positive semi-definite matrix. Just now to combine, to build a kernel on this space, we can simply combine one-dimensional kernels. So it's not the only way, of course, to build a kernel, but it is one. And for instance, we can use the well-known tensor-product operation, but there are other operations that you can use, like the sum, or the ANOVA one. ANOVA is defined like that. And if, so to obtain finally a kernel like that, we combine continuous kernel on one-dimensional spaces and so matrices, positive semi-definite matrices for the categorical variables. Okay. So we recover doing so, we recover the usual kernels used in computer experiments when we have categorical inputs. So people usually do tensor-product. We have found a paper also using a sum, things like that. Of course, you can do something different. For instance, instead of doing a product of one-dimensional kernel, you can use a kernel involving a distance. So you can use a metric, plug in into a suitable kernel. So there are alternatives to these constructions, but in this talk we will restrict to this construction here. Also, what you can do is to change the kind of operations. Here you can have a product, here a sum, and so on. Okay, just to give an example, a very basic example, what that does mean on the example above. If you want to define the covariance between two design points and blue and red, so what is the correlation between this point and this one, for instance? We say that it is the covariance between the spatial covariance between x and x prime times the covariance between blue and red. So, for instance, 0, 9. Okay. And once you define the covariance between blue and red, this number is used for every spatial x and x prime. Okay. This is what is done here. Okay. So now, when you have kernels with ordinal variables, so the idea, if you have an order, like here, so instead of using blue, red, I use integers, 1, 2, and so on. You know that you have a natural order. What you can do now is to define a distance between 1 and 2, 2 and 3, and this is the only question. And this can be done with a transformation, so monotonic transformation. For instance, if you think that there are the same distance from each other, then you can use this identity transformation. If you think that 1 and 2 are more distant than 5 and 6, you can use this transformation, and so on. And the general way, so, is to build a kernel like that. So you take a continuous kernel, and you apply it at the value obtained with this transformation. Okay. So behind that, there is just a Gaussian process that you evaluate at the f of x, at the image of x by your transformation, and this gives this kernel. So an important remark is that most usual continuous kernels like square exponential, math and kernels, give positive values. So when you do so, you will obtain positive correlations. Okay, now in the general case, if you don't have any order, the only thing that you can do to define a valid covariance matrix. And so there are several propositions for doing so. You can have a parameterization which is very general, using either the spectral decomposition or the Cholesky decomposition. And you can parameterize these transforms. For instance, for Cholesky, when you have a correlation matrix, it gives you points on the sphere. So you can use a spherical parameterization for L, and it gives you a matrix T. Also, you can, maybe in some context, and especially in our context, we aim at using less parameters, so they are using parsimonious parameterization. Probably the most simple one, the simplest one, is to use a compound symmetry when you have only two parameters, a variance for the diagonal, and a covariance, which is the same for all levels. So it means correspond to exchangeable variables. So you have only two parameters. You can generalize a little bit this matrix by saying that you have groups, and you have within group correlation and between group correlations. So this is what we are going to explore now. So first, try examples to understand how it works. So imagine that we have the same example as before. So one input which is continuous, one input categorical with three levels. So we propose to study how we can recover these curves using that kind of design. So we use a stratified design because we think that this point can give information for the other levels. So we use 5 points per level, and then we estimate and we compare with the true value of these curves. And the design is a random one, so we change the design at random, and we compute the Q2 criterion, which is analogous to R2 on a test set. Okay, so we aim this criterion to be close to 1. So for instance, if we do independent kriging, so we do 3 different kriging for each level. So it's, of course, it's not a good idea here because we have a strong correlation between levels, and we do not take it into account. So to do kriging, we have 5 points only per level. And you see it's a sinus form, so it's not so many. And the result is that the Q square is rather small, and with a large variability depending on the design. Now, when you have a common correlation between levels, which is a compound symmetry structure, we obtain a much better score. And for a general parameterization, you obtain a good score as well, with more variability. And the best result is used when you take into account both, we use a general structure for correlation, but also you take into account the fact that you have a different variance per level. So this is something that you can include very easily here, because you have a matrix, which is a matrix of size 3, because we have 3 levels. So it's not hard to add 2 parameters more by saying that you have 3 terms on diagonal rather than 1. So this is what we did. Okay, and we can have a look at the correlation parameters. So this is our matrix, correlation matrix. And we can see that for compound symmetry, so there is one common correlation parameter. The model estimated as negative, which is logical in a sense because the correlation is negative between black and red, between green and red, and then positive between red and black. So there are two negatives, one positive. If you say you have the choice, you must choose between this. On average, it's negative. Okay. And then the model with heteroscedasticity capture the good value for correlation, the good signs. And surprisingly, when you then take into account the difference of variances, you may estimate wrong correlations. So this is positive value is not estimated well here on this experiment. Okay. And if you have questions now, I can answer. Yes.
This structure you chose for your mixed camera, right? You showed this the matrices times t. What's the dimension of U? There is like the actual dimension of your classes, or you're using like one of k encoding of the classes?
I mean here.
Yeah.
Here you have only one-dimensional inputs, so you have several U. U is for a single categorical input. Okay, so for each input, you have a covariance matrix, and you combine them.
But U is the actual, this set you put there, you're not doing like one of k encoding, like binary encoding of the class.
No, I'm not using a binary coding. This is of course something that we can do, but not here.
Excuse me. So for your, after you take the product, so your covariance becomes the dimension of your continuous times the dimension
Exactly.
of your
Exactly.
categorical, but
Exactly.
there was
It's
like
not double
huge
U.
categorical values, so it becomes a very big covariance, I guess. If you have like, so let's say if you have 100 continuous points and then for the periodic table you have 100 categorical variables, then the product kernel becomes like.
Actually, we just need to know these matrices. We don't store in a big
Okay.
matrices.
Okay, that's what I'm asking.
Yes. No, we don't need to store.
Okay.
Okay. So now I'll show you what we can do with block covariance matrices. So we consider a block covariance matrix of this form. So we have diagonal blocks that model the correlation within a group. And we have off-diagonal blocks that give you the correlation between groups. And so usually what is proposed is to have a constant correlation between groups. So this matrix, this block matrix here, is constant. It only contains a single number, which is the covariance between the groups, which are different. Now, inside the group, so within the group, usually people use a compound symmetry. So reason for that is to say if levels are in the same group, they are probably positively correlated, or they have the same correlations. But as we saw in previous examples, it may happen that this is not true. So we may need something more general within the group. So we will do that. And actually, we need a condition. I will explain to you why. We need a condition which is general. It means that when you remove the mean to the within block, it remains positive semi-definite. Okay. So of course, for this matrix T to be a covariance matrix, you need this matrix to be positive semi-definite. In particular, the diagonal blocks should be positive semi-definite. Here we want a little bit more. When we remove the mean, which is a positive value, it remains positive semi-definite. And if you think to this condition, it is actually quite general, because the dimension of the block here corresponds to the dimension of positive semi-definite matrices. So d minus 1 divided by 2, something like that. And here you just remove one dimension by adding this constraint. So you can handle a lot of matrices. Okay, now the first result is that the block matrix that we, of the form, the previous form is valid if only if a small matrix is valid. The small matrix, you obtain it by simply averaging each block. Okay, so it's small size. Imagine that we have 90 levels here, but only 5 groups. This will be our case. Instead of checking the validity of a matrix of size 90, just have to check it for a matrix of size 5. Okay. So, in one sense, it is obvious, because if T is positive definite, it is a covariance of some vector, and actually the block average matrix corresponds to the coverage of the center in each group. So you just compute the average in each group, and the covariance matrix of this average gives you this matrix, so the small matrix. Now for the converse, actually it is because we have our assumption. You can decompose the block covariance matrix by a sum obtained by computing the average of each block and filling it with a good size. Okay, so this is the parenthesis here. And what remains, of course, for the off-diagonal blocks, because they are constant, you have everything, so it remains 0. And the diagonal blocks, you have the difference between the matrix and its average. And because we assume that this is positive semi-definite, this block matrix is positive semi-definite, and this one as well, because the assumption is that the small matrix is positive semi-definite, and when we fill the numbers, just an embedding. So it's preserve positive semi-definite. Okay, this is an algebraic view, but we will have more information by considering what is behind this matrix. And this is a probabilistic point of view, this is a modeling view. So actually this matrix corresponds to a model like that, which is a hierarchical model. When you have the effect of a group plus the effect of a level in the group. Okay, so we have normality assumption and usual independence assumption. This is what we usually call nested two-way ANOVA model, things like that, with Gaussian priors. And actually we need to add something, because if you consider only this, when you are computing the covariance matrix, you just add variances, and so you keep only positive correlation. You get only positive correlation. So to obtain the general structure, we need to add the condition that the average of the levels in the groups are 0. So the sum of the level in the group is 0. This is also a usual assumption in ANOVA models, because this is an assumption required if you want to identify the parameters. So, given these assumptions, the covariance matrix of eta, so the effect of the global effect, exactly correspond to valid covariance matrix of the form that we presented. Okay? And we can compute also the form of the diagonal blocks. So they correspond to the covariance matrix of the groups plus something given by the levels. And the between groups are given simply by the off-diagonal value for the groups. And what we have to understand is that this matrix here corresponds to a covariance matrix given a centering condition. So it is a centered matrix. It will be useful to study that. So first remark, if we consider the class of compound symmetry covariance matrices, By doing so, by adding the constraints at the level sum to 0, you recover all the range of negative correlations. Otherwise, you only have positive correlations. And now the center matrix FG can be parameterized. Actually, it is this matrix is just a general covariance matrix with the condition that the average is 0. So you can obtain it like this. You consider a matrix whose columns form an orthonormal basis of the orthogonal of 1. Orthogonal of 1 because it corresponds to the condition that the sum is 0. So it is m times m minus 1 matrix, and you obtain it like this by combining a general covariance matrix but of size m minus 1 and then extending it to size m. And this A matrix are known, well, there are examples in that are well known, which are named Elmert contrast matrix. So you have the form here. But it's not important, you can choose any matrix that respects this condition. Okay, so maybe this slide is too technical, so I switch. Now I show you some application on the toy example, on a toy example. So here I have more levels. I have 13 levels. And you can see that there are two main groups. You have groups with 9 levels and groups with 4 levels. And so we study what happens when you use this information in your kernel. So we take, again, I think 3 levels, 3 design points per level, and in a stratified way. So we have 39 points to predict. So now if you, so we study different strategy. First, we consider that every levels are in the same group with a compound symmetry structure. So there are only, of course it's very rigid. You say that you have only one correlation for everybody. And the result is not so good. Prediction Q square is less than 0.4. Now if you group 2 groups, and if you give the 2 good groups, you obtain a very good prediction. Now also what we try is that to say that, okay, we have this group, but maybe we can have 4 different groups here. So we don't gather them. And we have 2 strategies. This one is the most flexible one. And this one, here you say that you have the same correlation for 2 different groups. So same between group correlation for all pairs of groups. Okay? Because we want to have less parameters. But if you do so, you lose in terms of prediction accuracy. So you are less accurate. If you use the most flexible form, then you have very good results, as well as good results as for 2 groups. If you don't group the levels, what's happening? So you have 13 groups. You have a crazy number of parameters, 81. Recall that you have only 39 design points. And of course, well, it's not so, surprisingly, it's not so bad, because you have so many parameters, but of course, highly variable. And finally, what is maybe surprising in a way, but when you use the ordinal kernel to consider the levels are ordered, then it gives also very good results, but with more variability. So now if we have a look at the correlation estimated by the models, then we can see that when you say that everybody has the same correlation, the estimated correlation is approximately 0, because you have a mixture of positive value, negative value. Now for 2 groups, you recover well that within a group you have positive correlation and between a negative one, with strong values. For 5 groups, when you constrain the between group correlations to have a common value. It finds that it is negative, and of course it doesn't see that here, it cannot see because you use only one parameter, that inside here it is highly positive and outside it is negative. So it is a trade-off between the two. With 5 groups, it gives you the right signs. With certain groups, we observe that it behaves rather well, but of course there are so many parameters that the hyperparameter estimation of hyperparameters is erratic. And for ordinal, recall that ordinal you cannot find negative correlations with because it uses continuous kernels which have positive values. And so it recovers well what is within a group, but not well what is between. Now I'll show you the result for the case study. So for the case study, recall that we have four continuous inputs, 3 categorical inputs, the form with 3 levels, chemical elements, 94, and the energy with 6 levels. So the full data set that will contain both the training set and the test set, we build it like that. We want to have 3 points for each of the combination of levels of the categorical inputs. Okay? So it is a kind of stratification. So it gives you a size of more than 5,000 points. So it took a while to compute the value with the simulator, but we did it. And for the continuous input, so this gives you the 3 columns in the designs. You have 4 other columns for the continuous inputs. For this one, we use a Latin hypercube of size A. And from this big design, we extracted a small design to learn in a way that you have 3 points for each of the 94 levels of the chemical element. So now some exploratory analysis. First, we plot the output, which is in log scale, for the different levels of energy, and we recover the idea that it is the energy is an ordinal variable. So we model it like it. For geometry shape, the levels seem approximately exchangeable, so we use a compound symmetry covariance matrix. Now, if you plot the output versus the chemical elements, we find this. So the experts define groups. They define 5 groups. And we see at least that there is something rather consistent with this graph. We see that for the 5th groups, there is a much larger variance than for the 2 first ones, and so on. So the variance is different for each group. So in our model, we take this into account. So we choose a variance coefficient which is different for each group. And we use this split provided by experts. And so this is the results. So we investigate different kind of operations, the usual product operation in red, the ANOVA operation in the sum. It is the Q squared values. So, and there are 4 graphs corresponding to different strategy. A compound symmetry for chemical elements, using the 5 groups provided by experts with a common between group coefficient, and a flexible parameterization with 5 groups. And finally, ordinal kernel. So what we see is that using the sum as an operation is not suitable for this problem. Using the ANOVA seems to be the best way here. It is very close to using the product in terms of accuracy, but it's more robust to design variability. So it is something that we may prefer it, although it has more parameters, using an ANOVA kernel at 5 parameters here compared to the product, because we have 5 rules. Now, if we go into details, what the funny thing is that, of course, when we use a group, we find better results. And the funny thing is that the best result is obtained with an ordinal kernel, which was not clear for experts. The experts were not betting for that. They did not consider that chemical elements was ordinal variable for this problem, but we find it. Of course, it is somewhat disappointing for what we aim at finding. But it's like that. I mean, it's real life. And this is explained by the fact that, sorry, I don't have the good figure here. Because usually we see that there are strong positive correlations that are decreasing when we have groups. Well, the correlation should decrease, should be low between this group and this group, and stronger with this group again. So I don't have the good graph, sorry for that. Maybe I go to the conclusions. So some general conclusion for when we use categorical variables in a Gaussian process. First, have in mind that a kernel on a discrete space is just a matrix, positive semi-definite matrix. So it's not complicated. You can build kernels using a product, but also other operation, sum and ANOVA, which is more flexible, have more parameters, but more general. You can use warping operation. It was used for the ordinal case, and there are other ones. Also, you can handle heteroscedasticity just by choosing the diagonal coefficient in the matrix. So something easy to do. For group covariance functions, we have several results. First, in a very general way, the block covariance matrix is valid if a very small matrix is valid, obtained by just averaging each block. Second thing, it corresponds to a probabilistic model, which is a hierarchical model, and where level effects sum to 0. And with this condition, you can recover negative correlation within a group. And notice that if you consider a multi-resolution Gaussian process or tree Gaussian process, things like that, you only have an independence assumption that the children are independent conditionally on the father. It means that the levels here should be independent conditionally on the group. And here, due to this assumption that the level effect sum to 0, it is not true. So it is a difference with that kind of models. Also, what is important is that we obtain a parameterization. So actually, we don't need to check that a small matrix is positive definite. If we start to parameterize the matrix, there are some. This result is useful anyway because it's not obvious to obtain a parameterization of homoscedastic matrix. Like that. When you parameterize the matrix, you obtain a matrix that has a good form, but when you require constraints more than that, it's not easy to check. So the two results are interesting. So we use R packages, mixgp and kergp. Kergp is already available on C1, but we need the recent developments are not included in it, so we will release them soon in the next few weeks. Finally, of course, there are some questions that we may consider for perspective. How can we include trend in GPs when we have categorical inputs? So here we may use strategies coming from linear models. It is very common. how can we group levels? Because here the levels were provided by experts. How can we group them? So maybe an element of answer is also provided by linear models. Because for linear models, we have strategies based on L1 penalty. So there are variants of lasso technique to find groups. So maybe we can start from this research. And also, how can we order levels? Sometimes it's obvious for the chemical element variable, it is given by the order of the chemical elements. But is it always like that? We don't know. And finally, if you want to perform optimization with ego strategy or another strategy, where we have those continuous and categorical inputs, it is not so obvious to find a good optimizer for that. The optimizers for continuous inputs, there are also a different class of optimizer for discrete inputs, but when you mix them, I think it is a way of research to find a good optimizer. It's not so well investigated. Yes, so thank you very much for
We have time for a few questions. Yes.
Hi, sorry, I think I might have just missed what you crucially said, but in the nominal case, the ordinal was working well. I assume that's because the levels within every group were consecutive. So you'd have to do some sort of pre-processing to get that to happen. So in your 91 levels, all the groups were 1 to 10, 11 to 30.
Yes.
Which seems like that might be why the ordinal worked well. Yeah.
Yes, in this case, it seems that the groups corresponds to an order.
Yes.
Yes.
So you could perhaps pre-process to get that.
You mean I can include this information in my kernel?
Yeah. So what I was thinking of is different regions of the world, and if you were to just number them according to longitude or latitude, you wouldn't get a grouping that would work in an ordinal sense. But if you were to do something like polluted levels against land and sea, then you could order them in that way. And then the ordinal might work even though they're technically normal. As a pre-processing step.
It's worth saying, I think I'm right in saying, sorry, Carol, but this is atomic number.
Yes.
Yeah.
So there is a natural order. The periodic table is one of my. It's square, so it's a bit like longitude and latitude.
Yes. Yes, but again, it was not obvious for the experts that this natural order of chemical elements was relevant for the kind of application. I mean, is there any reason for this order to have a link to the output that you consider here? It was not so clear before trying.
I think just following up on this, I'm tremendously lazy, so if I was doing this problem, I would just say, right, I'm just going to say that the atomic number is a continuous variable and see what happens. Have you tried?
Yes, definitely. Oh, sorry. It's here. It's ordinal. It's like a continuous.
It's like continuous, but it's not quite continuous, right?
We use warping to adapt.
On the atomic.
On the atomic number.
But I would just use the atomic number, just use it.
Like 1, 2, 3, 4, 94? Yes, but what we did is better.
Well, yeah, sure.
Because we estimate the warping.
That's what you get for being lazy.
We estimate the transformation because when you do that, when you do 1, 2, 3, 4, you say that the distance between 1 and 2 is the same as 2 and 3 and so on. Here we estimated the transformation.
So you just weren't lazy at all, and you went straight to doing the good stuff.
So there's no figure like that with 1, 2, 3, 4.
I do recommend not
follow-up
doing
question on that. So 94 levels, you can do this. If you had 10,000 levels, you would do what JP well, I would certainly do what JP is suggesting and just pretend it was continuous and maybe split it up later. Or 100,000. I mean, there must be some number where this becomes not worth it, and we just pretend it's a continuous variable.
In my opinion, you can do what you say, but you also can do a hierarchical model with more layers. Here you have groups, levels. You can have groups, subgroups, and levels. And you can deal with a small number of parameters to consider numerous levels, because the number of parameters will be the number of parameters, yes, will be as a function of the log of the size.
Okay, so the important thing is the number of groups, not the number of
Yes.
levels.
Number
Okay,
of
so if the
groups.
number of groups got to 94 or 100 or something, it becomes not worth it.
Yes, you have an okay. It's a very large dimension.
Yes.
I have like two questions, one simple one. Did you find the same sort of results when comparing marginal likelihoods as well? So when you optimize like your hyperparameters, you get the negative log marginal likelihood. So did you see that the ordinal one is giving best negative marginal likelihood?
Oh, we say so we estimated parameters by likelihood.
Yeah, so I was just asking how was the likelihood comparison? Was that agreeing to these results or like?
I don't know.
Okay.
I'm sure we have the result somewhere, but
Okay, I mean like that's a simple way of model comparison because
yes, you
I
mean
kind of see this problem as a model comparison problem, so obviously comparing the marginal likelihood. But anyways,
Good idea.
Yes.
and the second, it's just a opinion I want to ask you. I mean like, let's say what Peter was saying, like you have 10,000 levels, that's a difficult problem. But also I mean like, what's your opinion on, let's say I have a multitask problem where I don't have categorical inputs, but let's say I have 10 outputs, and I can reframe that problem as a categorical input problem. So can I use this methodology in that case?
I think
So
so.
what do you suggest?
I think so. You can use it.
Oh.
Actually, the example that I show at the beginning with three curves, a red one,
Yeah, exactly.
a
That's
blue,
what
and
I'm saying.
a green, can correspond to three outputs.
Yeah, because like I kind of try to fit this sort of couple differential equations, and I think these sort of things can be used.
Yes, I think it's
Just
you can use
pretending
exactly
them
that.
as like one another input.
Actually, in the literature, we found links with multi-output
Multitask
Gaussian
GPs,
process.
yeah.
It's very connected. Yes.
Thanks.
If there's no other question, I have a question.
Yeah. Just with your question about, so the way I understood it, the mapping between levels, set of levels and the partition, which are your groups, you cannot leave it as a free thing that provides an input on your program that you could optimize, etc. But is it really the case? Because since you already have a covariance structure there, can you just do clustering and find the actual groups that are consistent with the covariance structure?
This is a good question. That you mean I probably don't know in advance how many groups we have, and so we do a clustering to.
Yeah, because you have the covariance structure, you put the covariance structure. So you will not know how many groups, but how you split them, you will know, yeah, because of your covariance structure.
Well, we did not investigate, but this is something we have to do, of course.
I have a question.
You can ask the question.
So you assume that you have a constant correlation across groups, right?
Yes, between blocks.
Yes, between blocks. Yes.
Between blocks.
So would it be very difficult to go for a varying correlation across groups? Let's say some regions of the input space, in some regions of the input space, you may have a strong correlation between those groups, and in some other regions you may not.
Good question.
I don't know if
Very
it helps also if it's...
The idea here was to use a parsimonious parameterization.
Yes.
So to have a single number,
Yeah.
to say what is between different groups. If we have something more complex, it's a very good question because I don't know the condition. If there is a simple condition to ensure the validity of the block covariance matrix that Of course, you can propose a lot of different off-diagonal forms, but can we obtain a simple calculation of that or a parameterization of such matrices? This is the aim. At least what we can always do is to propose the form of covariance matrix, general, very general one, with specified off-diagonal forms, and then do optimize our parameters with constraining that this matrix is positive semi-definite. So this one, you can always do that. This is a very good question, actually. I don't know the answer.
Just a follow-up question. Did you use quasi-Newton to optimize the parameter? Conjugate gradients or?
I simply used different optimizers, and this one is maybe Cobila.
Okay.
We use multi-start also because it is a difficult
Yeah,
optimization
that's what
problem.
I'm asking.
Yes.
So I think we are just in time.
Yeah, just something I want to add. Well, no.